Okay, so today we're going to talk about matrix multiplication, matrix vector multiplication, vector matrix multiplication, and that will be the first recording that we do. So let's go ahead and get into it. Now, we need to start with, so we're going to say maybe let A be a M by N matrix. And let's say X be a N vector. Our goal is to completely understand this multiplication. It's like the most famous looking equation of all linear algebra courses. It's just matrix A times a vector gives you B. Okay. Now, if you look at how this is defined in a textbook, more than likely you're going to see something that's pretty gross. Let me see. I'm curious how they do it here. So actually they don't. This book does it well. This is not what you would normally see, so I'm not going to write that in. But if you look up the definition of matrix vector multiplication, it's going to be, it's going to look a little odd. It's got a summation formula, and I think of it as not the best description in most textbooks that I've seen. So what is this? Okay, so what is a matrix times a vector? This is the most important concept. This is a linear combination of the columns of A. So by that I mean, like, if A is equal to it's in columns. So if A looks like that, then A times X is equal to X1 times A1 plus X2 times A2 plus dot plus Xn times An. Okay, so this is what I mean by a linear combination of the columns. It's just like the linear functions that we were looking at earlier in the semester. Okay, so yeah, I think maybe we should just do like an example so you can see. Let's take this matrix here and multiply it by, I don't know, maybe a half, 2, and 3, or something like that. So this product, I'm curious if y'all can guess, based off of just this definition here, this notation mainly, can you guess like what this is going to be? Well, it's obviously it's going to be a vector because this is this becomes a sum of vectors, so it's a vector, but what are the entries of this vector? That might be too much to ask.
Two rows and one column. Is that what you're asking? A vector.
Yeah, so it's gonna be two rows and one column. So let's look exactly what it'll be. So we have a half times the first column plus 2 times the second column plus 3 times the third column. And this is going to be 1 here, right? Just scalar times vector plus 8 and 2 plus 9 and 0. Okay, and what is this going to be? 18 and 3. Okay, so that's not so bad, right? Like that. This is why I'm a fan of thinking in matrices as column vectors, because when you start looking at multiplication, it's easier to keep track. It's easier to do in my head the linear combination of the columns than the other ways that can be presented. Okay, so actually maybe let me just put up like another example. What do you think about that?
Is it not possible to do?
Not possible, right? If it's going to be a linear combination of the columns of A, there needs to be at least the same number. There needs to be the same number of things in here as there are columns in the matrix. So like that would not be possible. It's not defined. What do you think about this product? What do you think that's going to give you? You should be able to do it like immediately. If you understand that it's a combination of the columns, it's like immediate.
One column and 3 rows.
Yeah, but what's the vector? You can just tell me the vector immediately. I know we were just now introducing it, but think about it. What are those zeros going to do? They're going to be
summing the rows or
0, right?
First question was about the rows. What was that?
I was saying, were you summing the rows or summing the columns to get like the one? You're just timesing by ones, right? And then you would just sum.
Right. So
sorry.
Yeah. But I'll get to that in a second. In the second question or comment.
I was saying like for the 2 bottom zeros, when you're multiplying, won't they just go out to 0?
Right, which means what will you be left over with?
But just so it's going to be 0, 1, 2. I think okay.
That's it. That's it. It's just the first column. Because if you think of this as if you think about what's happening here, it's just 1 times the first column, right? Plus 0 times the second column. Doesn't matter. Whatever's in there, it doesn't matter because it's just going to go to 0. Plus 0 of the third column. So that goes to 0, that goes to 0. You're just left with the first column. That's what I was like trying to like get you to say out loud, like, or to realize is that this multiplication is just picking out the first column.
If we were multiplying by a row vector, that's that same column vector, but it was a row vector. So it's like
actually not. We haven't got there yet.
okay.
All right. We only. By the way, row vectors. So every vector that I ever write down is taken to be in column form. If I write down a row vector, I'm always going to say that it's been transposed. Always. That's like kind of standard for a lot of textbooks, that row vectors are like column vectors transposed. So column vectors are like the very beginning of how the vectors live, if that makes any sense. But we'll get to that, what you were talking about, the multiplying by a row vector in a moment.
Okay.
Okay, so again, just to make sure everyone understands, without even thinking, what's the answer to that? What's the vector?
It's 3, 4, 1.
Exactly. Exactly. Okay. So what about, what would I multiply? So suppose I wanted to add the first and last vectors together of a matrix. What vector would I multiply to add those together?
1, 0, and 1.
Yep. 1, 0, 1. Okay, this is good. This is going good so far. Because playing around with this and understanding that we can add the columns together by multiplication, understanding that is crucial to a lot of linear algebra. Okay, so let's think about this some more. This is a fun game for me. I'm enjoying this. Suppose we wanted, no. Suppose we wanted to average all the entries in the matrix. One way that we could do that, if we already know to average the entries of a vector, would be which would give you some vector, and then you could just divide that by n times m, right? Or in this case, 9. And that would give you like an average vector of the entries in that matrix. Okay. So I think, we now get to understand we finally get to understand the inner product. So if like A is equal to 1, 2, 1, and B is equal to 2, 0, 1 or something, we finally can understand why we write this the way we do. So this is a 3 by 1 matrix, and this is a 3 by 1 matrix, right? So the transpose of a 3 by 1 matrix is a 1 by 3 matrix. It becomes a row. So now, this is a matrix vector multiplication, just like this, right? So what is this matrix vector multiplication going to be? It's going to be 2 times that column plus 0 times that column plus 1 times that column, right? So that'd be what, 3? And like you do get like a 1-by-1 vector out of it, but a 1-by-1 matrix is just, or vector is just a number, so it's just 3. But that's why we use the notation that T, because the inner product between two vectors is the same thing as a matrix vector multiplication. Okay. So hopefully all of this is making you're understanding what's happening right now. Okay, I want to see if I can guide you to the definition of matrix multiplication now. Okay, so matrix multiplication, and so again, you know that I like my columns, my column view. Now, as I've mentioned before, vectors are just a special case of matrices. Vectors are just a matrix with a single column. So if we're looking at a matrix multiplication, right? We already know how to do it with one column. But what about if there's more than one? Can you guess? I don't know the chances of you getting it right. I'm very curious. Can you guess what the size of this resulting matrix will be? Okay. Can you guess the size? Also, how many rows? Okay, that's the first question. How many rows must the matrix B have? How many rows? N, right? Like, remember that the number of rows in the vector needs to match the number of columns in the matrix. So this matrix better have n rows for sure. Because the special case for vectors, it must have n rows. Okay. So if that matrix has n rows, what do you think the resulting size is going to be? If we multiply an n, let's just say that this is a m by n matrix is A. So this is m by n, and B is n by 2. What do you think the output is going to be?
2 by n.
Well, let's see what happens. Well, I'll just go ahead and say it's not n by n, but can you guess again?
Then n by 2.
Oh, okay, correct. It's going to be an n by 2, right? So I think about when we did matrix vector multiplication, right? We had m by n times a n by 1 gave us a n by 1, right? So yeah, this is going to be an n by 2. And what do you think? How do you think that we can express this? Like, if it's an n by 2, then there's going to be 2 columns, and you know how I like my columns. what do you think the first column is going to be? And again, these are all guesses. I'm just seeing if you can like play this game with me. So how did you get so when you do matrix vector, how did you get the first column of the output? There's only one output column, but how did you get that column? Like, what is this? This is,
Is it the multiple?
that's the matrix times that column, right? So if this is X, and this is, all of this thing is A, right? A times this column gave you this column. So if this is all A, right? Maybe I can give you some more hints now. This is just all A. So what do you think the first column is going to be here? And they're really like, it really is a guess at this point for you guys, but just, I'm trying to like associate the patterns here. A times X gave you the first column here. So what's the first column going to be here if there's two?
AB1.
Exactly. So say it exactly. A times B1.
Yeah.
How do you get the second column?
A times B2.
Exactly. A times B2. That's it. What if there were a bunch of, like, what if there were like K columns? What would the size of the output be? If B had 2 columns and it was a what? It was an n by 2, right? If B has K columns, it's going to be a
N by K.
right. Because each column multiplies A. B1 multiplies A goes right there. B2 multiplies A goes right there. Dot, dot, dot. BK multiplies A, and there it is. So I really want to like emphasize that in linear algebra courses, from my experience when I was a student to like TAing experience to teaching linear algebra courses, well, I haven't had the problem when I teach it, but I've observed other courses that are linear algebra. Matrix multiplication is very confusing for a lot of students because I don't think that that instructors emphasize that it really is, once you understand matrix column as like a matrix vector multiplication as a linear combination of the columns of A, you just have that in your head. Then when you start looking at matrix multiplication, you can make sense of what size the dimensions have to be, because you know that since this is going to be a linear combination of the columns of A, this better have n rows, just like y'all pointed out, right? And it doesn't matter how many columns it has, but it has to have n rows. And just those things have to match up, and your output is going to be the number of rows and the number of columns there. Okay. Okay, so we should do a numerical example to kind of like emphasize this. Okay, so take a moment to actually let me make it a little bit like easier. Yeah, just so you can maybe do it in your head. Make that 3 a 0. So what's the first column going to be? That should be easy of the output. It should be easy. I think everyone here should be able to say it. What's the first column there? How do I know that it's 6, 4, 2? Without even like thinking more than a second.
Because you're multiplying the 2 with the everything in the first column.
Right, exactly. It's just like when you look at it, just think twice the first column and nothing from the other columns, because that's a 0 and that's a 0. Twice from the first column, nothing from the other columns. So 6, 4, 2. The other one's a little bit more difficult. Maybe maybe I'll put a 0 right there. What's the second column? You can probably do it in your head, right? How do I know the first entry is going to be 5? It's 1 of the first column, 0 of the second column, twice the last column. So 1 of that plus 2 of that. So 1 of that plus 2 times that is a 5. 1 of that plus 2 times that is a 2. 1 of that plus 2 times that is a 9. Is that somewhat clear? Do you understand this?
Yeah, it's clear.
Yeah, I think I'll probably do more examples.
Yeah, yeah. So let's keep on playing with it. Okay. So notice how when I put a 1 there, right? I was taking 1 of that column and then I put a 0 there, so I excluded that column and I put a 2 there, so that I put 1 column here with 2 of those, and then I put them together, and that's the last entry, right? Okay, this is actually, I've never done this with students because I've never had a class this small. But I want us to play a game called Make the Matrix. So now I'm going to give you the output, and I want you to think of what to put here to get the output. So first output is this. Okay. What can I put there to make that?
Is that going to be a matrix or a vector of ones, matrix of ones? Excuse me.
Well, you have to be careful though, right? Like if I put a 1, 1, 1 right there, what is that for this first column? Would that give me the right answer? 1 of that column plus 1 of that column plus 1 of that column would definitely be way more than 3, 2, 1, because already that's 3, 2, 1.
Would it be like one's diagonally and then zeros above and below or something like that?
Yeah.
That's it. That's it. Y'all knew that there had to be ones. It was just how you're going to put them in there. You had to like think about it, right? So why does this work? Well, when you form the first column here, you take 1 of that column, 0 of that one, and 0 of that one. So remember how we were over there, we were choosing just the first column? That's kind of why I was doing that earlier. This vector times this matrix is picking out the first column. This vector is picking out the second column. 0 of that plus 1 of that plus 0 of that. This vector is picking out the last one. Right there. So this is why these types of matrices are called the identity matrix. Because when you multiply by an identity matrix, you get back the original matrix. Okay. All right. So now let's play this game again. Let's see. I do it too big. Running out of room. Two, 104. All right, so let me think of an interesting one. Maybe, what can I do? Maybe, let's see. So when playing around with this game of making a new matrix, right? We've learned that like these special vectors like this, right, with the ones in a certain place, will pick out a given vector, right? But if that was like a 2, it would pick out like twice of that. If it was a -3, it would pick out -3 of that. So I'm curious if we can multiply by a matrix. It definitely puts a 1 right there. And definitely puts a 1 right there. I don't care what's left in that matrix, but I want a 1 right there and a 1 right there. So what can I multiply by to do that? They're not going to be whole numbers, by the way.
Be 1/3.
Where? Right here?
Top left, yeah.
And then it doesn't really matter what's underneath it, right?
No.
I guess if I wanted like zeros everywhere else, like, could I do that? Is it possible? 1/3 of that, no, I don't think that's possible. But yeah, there would definitely be a 1/3 there, and there'd be a 1/4 here. Okay, so I think I've kind of like exhausted the matrix interpretation in the column form for this multiplication, which hopefully will now shed light on something brought up earlier. So if we have an n by m matrix, and we try to multiply it by a row vector, is that possible?
Yeah.
Well, if you think about it, how many rows need to be in this?
M.
Yeah, but this is just a vector. Like if that's just a row vector, you can't do it because there's only one row, right? Like 2 or something. There's only one row, but there's going to be more than one column in that matrix, so you can't do matrix row multiplication. However, you can do, or can you? It depends on the size of the things. So if you have an M by N matrix here, can you do row matrix multiplication? Is that possible? And when is it possible? You have to think of this, even though it has one row, you have to think about it as a matrix. If it has like what number of columns do you need for this to make sense? For this
M.
matrix. I think I heard it. Say it again.
M.
M. Because if this matrix has m rows and this one has, if this matrix has m columns and this one has m rows, we're good to go. We can still define multiplication that way. So, okay, what is this going to look like? Like, if we have like x1, x2, dot, 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 xm, and we have a matrix now. We had, like, we might have to change this picture, but let's just suppose this is going on. What is this row going to do? What is a row times a column? A row times a column, we already know what that is. Remember the whole like row times a column? It's just a number, right? It's a number. So if we think of this as, so what is this going to be? This is going to be, how do we define it for? It's A1 times this whole thing. Like this whole thing could be like X, right? So if this has n columns, then this is going to be A1 times X goes in the first entry, and then A2 times X. Like that's, you're treating this like the matrix, like the matrix that we had up here before. Dot, dot, dot. Just do that for every column of that matrix. So row matrix multiplication gives you a row vector. You see that? It's a, because this is a 1 by m matrix, and this is a m by n. So the output is going to be 1 by n. Okay, and what is this row gonna like? How can we interpret this? Like a lot of linear algebra, because the computations can be very tedious to do when you have like large matrices. We should always strive to have like an interpretation of the things that we're doing. So here, it's like X is doing something to, oh, it's like, it's, what is it? It's like, how can we interpret this? Well, I do know that this row times that column, that's a number, right? Just a single number, and it goes right And this times that is just a single number, and it goes right there. So maybe if we have 2 rows, we can get a better idea, because just that one row is, it might be like a little throwing you off, because it's just producing this row vector. So what if we had like and so this is defined, right? So 2 by 3 by times a 3 by 3. So, oh, the output now, it's not going to be a single row. It's going to be 2 rows. It's going to be this row times this matrix is going to go right across here. And then this row times the matrix is going to go right here. So it's like, if X is that row, so it's like X transpose times A. And then here this would be like Y transpose times A. Now, because this whole row here, this is like X transpose times A. Is that row. So that row goes there. That times that, I mean, this row times A goes there. Second row times A goes here. So this is the row way to think about the multiplication. It's that now if I wrote like a third row, we can also think about more than just the so like if this is, so we have like, this is a big matrix B times A, or A times B. So let's say that this is a M by N matrix, and this is a K by M matrix. Then we can think of, so like maybe there's like X transpose, Y transpose, Z transpose, and like A1, A2, A3. Instead of thinking of, like in the very first matrix multiplication picture I drew, we thought of the columns over here. We thought vector times linear combination of the columns of the matrix on the left. But we can also think of it as filling so we can ignore the columns and just think of row matrix multiplication, where the rows of this matrix are the multiples of A times each row here. So it's a different way of interpreting matrix multiplication, but it's equally useful. And we'll see why in a moment. I should probably just, maybe I'll use that. I need like a good example matrix. Gotta be something in here. I'll just have to make one. Okay. And let's just see what this does. Now, but this is well defined. It has yeah, this is defined. Is it? So 1 times that plus 2 times that plus 3 times that. Yes. So the output's going to be, oh yeah, what is the output going to be here? Not numerically, but like what's the size of the output? We have a 2 by 3 over here, and we have a 3 by 3 over here. So what's the
It'll be-
output?
It'll be 2 by 3.
Right, it's going to be 2 rows and 3 columns, because you can do that column times the matrix goes right there. That column times the matrix goes right there, right? Just think about the column interpretation first if you get like mixed up. So now let's think about this in terms of rows. So when we perform row matrix multiplications, let's like focusing on, maybe I'll put like a 1 right there as well. So we're focusing in on this row right here. And that row times that matrix is somehow going to interplay over here. I erased it, but let's see how it does. So what's going to happen here? So yeah, we just focus in on it. I know this seems kind of like maybe I'm like going like I'm focusing on it too much or something, but this is a very important concept that a lot of students struggle with. I know that I did when I was a student. All right, so let's just think about this in the column way to get a sense of what's happening. So it's that times that, right? So what is that going to give us? It's 1 times 1 plus 2 times 1 plus 0 times 1. So it's going to give us a 3. Right? So, but what did that really do in the first entry? What did it do? It really, if you now, so this times that. But now let's switch our mind to think row times that. What's happening here? We're taking 1 of that entry, adding it with 1 of that entry, and 0 of that entry. Is that like clear now? Like switching over to this side instead of going like, I know that when I think column multiplication, I'm always on the left. When I think row, I move myself, I'm always on my right. I don't know if it's reflected on screen, but I hope you get what I'm saying. But think about it, 1 times that plus 1 times that plus 0 times that. I'm really just saying with this vector, I want to add that number and put it right there. That's what I'm saying. And so with that in mind, what's the second number there? Just thinking of it like that.
4.
Right. We're adding that and that. That's it. So it's 4. So what goes right there? Immediately. 4. So now we see that 3, 4, 4. Okay. So 3, 4, 4. And this entry right here, we got from these numbers. We said 1 there, gave us there. 1 there, gave us there. 1 there, gave us there. So what is this going to do in terms of row matrix multiplication? It's going to now only select what from each of the columns?
Top row.
It's just one of that one. It's just selecting those. That's all it's doing. It's going to be 1, 0, 3. It grabbed that row. Let's make sure, because I do mess up sometimes, because again, I prefer the column length. Let's make sure. So 1 of that, so 1 times that, plus 2 times that, plus 3 times that. So 3, 1, yeah. And then here, 0, 4, 2. So should be 4, 0. Perfect. Okay. Okay, so now why is this interpretation needed? Why am I emphasizing this so much? It's because if you understand how to grab things out of it by picking a matrix to multiply it by, you understand how to factor the matrix. You understand how to make it look a certain way and build a matrix that is nice. And we'll understand what nice is in a moment. But so how do we interpret that row? That row is just grabbing the first column and putting it right there. This row is grabbing the first column and adding it with the second column and putting it right there. You see that? I mean, that column, sorry, that was, this row is grabbing that row and adding it with that row. That's how you interpret that. Right? Just let's really emphasize that. This row is saying, I'm going to add 1 of that with 1 of that and 0 of that and put it right there. That's like a key importance. This row is saying in the second row entry, I'm just going to put the top one. Right? What would I put here if I wanted to add, the first row and last row together and none of the 0 row, what would I put right here to add the first and last rows of the matrix A?
1, 0, 1.
Exactly. What would I put? So if I did that 1, 0, 1, it would be 4, 2, and 5, right? 1 of that row and 1 of that row, add them together. So I hope you are taking good notes on this because it's not written like this in the textbook. What about if I wanted to make this a 3 by 3 matrix? And I wanted to, 100% for sure make a 0 right there and not affect any other entries in here. And if I wanted a 0 right there, how could I do that? With the idea in your head that you're allowed to select out the rows and put them together now, you know how to do that. You can take 1 of the first row and 1 of the last row and add them together, put them right there. So if you wanted to make a 0 right there, how could you do that? Come on, I hope someone gets it.
Would you put a 0 in the last entry of the first matrix?
So 0 right here?
Yeah,
So why would you put a 0 right there?
because that's picking the third row of the matrix.
and zeroing it out. But what if these are like non-zero numbers right here? Like if these are all 0, then yeah, there'll be a 0 there. But then you wouldn't, this would be like an empty row, it wouldn't matter, right? So what about if they can't all be 0? Like if this is like a 1, it doesn't matter what you put, like maybe it might, but like, remember that you're going to add the second row to 0 of that, so you'll still have like a 2 there, right? So don't think about putting zeros here. I'll give you a hint. Think about putting a negative number somewhere in there and a positive in another. That's the hint. There's going to be a negative and a positive.
A -1 and a +1 offset each other when they add.
So think about it. You want to add the rows together somehow to make a 0 right there. So what about if I put a -3 right there? That's another hint. Come on, someone's got to get it. I put a -3 right there. What's going to happen? What is it going to do? It's going to take -3 of that row, and you decide what else to put there to make a 0 right there. Hit someone. Come on. Don't disappoint me. What's that going to do? It's going to take -3 of this row, 0 of this row, and 1 of this row, and add them together. What's going to happen? What's -3 times that 1? It's -3. Added with 0, added with 3, it'll give you 0. -3 times that, plus that, it's just 2. -3 times that, plus that, is -7. But there's a 0 there for sure. Do you see what I did? Like, do you see how, like, I saw that there was a 1 right there, and I made that into a 0. What about, now that you've seen that business?
So is this kind of similar to like the row operations or like the reduced row?
You're right. You're definitely right. I was trying to avoid that conversation, but yes, you're right. What if I want to make a 0 right here? What can I pick out? What row should I put here to make a 0 right there? Ah, come on. You're adding the rows by picking the numbers.
You could put a -3 again in the first column, second row.
But there's a 2 there. Then you'd have -3 times that plus.
Oh, okay, never mind.
Come on, I know someone's gonna get it. Come on. How did I do it here? To make a 0 on the third row, and that's a 3, I put a -3 there, and I put a 1 in the last entry and a 0 in the middle. So I take 3 of that and add it with 1 of that. And I know that's going to make a 0 in that entry. So how do I do that to make a 0 in that entry now that there's a 2 there?
We'll just do a -1, 0, 2.
-1, 0, 2. So what would that do? -1, if like there's -1, 0, 2, that's -1 of this plus 0 of that plus 2 of that.
Right, never mind. I'm doing.
Yeah, it's like I understand the difficulty of like switching back and forth between row and column, but it's the most useful thing to understand. And that's why I'm trying so hard here. You're gonna all of you are gonna be bummed that I write it.
Is it -2?
Okay. Continue.
1.
That's it. -2, 1, 0. Why? Because you're taking.
Oh, because you want to match the one. Is that you want to like the one to be tight?
Yeah, well, you want, if I just told you to make that a 0 by fixing this row, you want to multiply that 1 by something that when you add to that 2 is going to make it go away. So 2 times that 1 and 1 times that 2 and 0 times the 3, it's adding -2 of that and 1 of that, -2 of that, 1 of that, -2 of that and 1 of that. Yeah, so -6 plus 1 is -5. Okay. Now, all right, so what do we have now? So So 1, 1, 0, -2, 1, 0, -3, 0, 1. And then this one was 1, 2, 3, 0, 4, 2, 3, 1, 2. And this product that we know has made 3, 0, I have 3. Why is there 3 right there? That's fine, whatever. 3, 4, 0, 4, minus 5, 0, 2, minus 7. Okay, so we know this is equal to that, right? So this in here is equal to this, okay? Now suppose we did this multiplication, and we looked at our matrix, and I even did it just now, and I was like, why is there 3 right there, right? I was just looking at that, like, I don't like that 3. I like it when there's 1s in the diagonal. I just like it. It's appealing. I like the identity matrix. I think they're cute. So let's now see if we can keep on multiplying this thing to get a 1 right there. I want that 3 to become a 1. And I know that this is all equal to this. So I want that 3 to become a 1. What can I do to do that? And I also want that 4 to be a 1. I want that to be a 1, and I want that to be a 1. What can I multiply by? It's really easy. If you think about the row picture, right? Whatever row you put right here, you're going to decide how you're going to take combinations of the rows of this matrix, right? So if I want a 1 right there, so like this product is not, like, I want to make that like, it's a temporary 3. If you haven't figured out what to multiply that by, it's a temporary 4.
You multiply it by 1/3.
Okay.
Get 1.
1/3 of the first row plus how many of the second row? None of the second row. Plus how many of the third row? None. So you could multiply 1/3 of the first row, 0 of the second row, and 0 of the third row. And what would that do? That would say 1/3. So, yeah, so this would become, that would become a 1. This would become 4/3, and this would become 4/3. Because you're taking 1/3 of that row, adding it with 0 of that and 0 of that, so it's just 1/3 of that whole row gives you that. So This was the choice to make that a 1. How do we turn that 4 into a 1? We want to turn the 4 into a 1 as well.
0, 1/4, 0.
Yes, exactly. 0, 1/4, 0. So you're going to take 0 of that row, 1/4 of that row, and 0 of that row. So that'll be 1, and then -5/4. And you know, because I want this to be like the identity matrix, I sort of want to make that a 1 eventually. But maybe first, I want to look at this and see if I can what can I do? Well, I can just not change anything and do this. Multiplying by that row is not going to change anything about the third row, right? It just takes 0 of the first row, 0 of the second row, and adds 1 of the last row, so I don't change anything. So this definitely gives me this product, okay? So let me go ahead and write that out. So currently our matrix looks like this. 1/3, 4/3, 0, 1, -5/4, 0, 2, -7. That's currently what our matrix looks like. So now, everything in yellow multiplied together is this, right? But I don't like that. Like I said, I prefer my matrices to be the identity. So the bottom row is throwing me off. I need to make that 2 a 0 for sure. How can I put a 0 right there? Like that 2 is bothering me. I don't like it. What can I multiply by? It's going to be a 3 by 3 matrix, but I just need to know one row to multiply by to make a 0 go right there. Somebody please tell me.
Can it be row 1 and
So this, it's really like we're multiplying on this, right? Like what do we multiply this by to put a 0 where that 2 is? It's gonna, I'll give you a hint, it's gonna be something on this row.
is it the first and third row? The second? Oh, like the number?
Yeah, so what numbers did I put on this last row to make that 2 go away?
0.
Okay. Then what? So you're taking 0 of this row plus what of this row plus what of that row, and you want to add them in a way that makes the 2 go away.
You can put -2 and then 1, maybe?
Perfect. Absolutely, that's it, right? Because there's a 1 sitting right there, it makes life easier to 0 out things below it, right? Actually, once there's a 1 there, I can make anything below it go away really easily, right? You just look at the number below the 1 and you say, oh, I need to take the negative of that number of the row where the 1 is and add it to 1 of the row where I want to make the 0. So, and what's also nice about this is that if there's zeros to the left of the 1, then you're not going to add anything, like there's still going to be zeros over here. So we took 0 of that, -2 of that, added to that, so there's a 0 right there, Negative 2 of that is positive 5 halves. So negative 7 plus 5 halves equals negative 2 plus 5 over 2. So negative 9 halves. Negative 9 halves. And okay, so the matrix that we can do to multiply by, if we only wanted to change that to be a 0, oh, wait a minute. If we can change that to be a 0, can we make that 4/3 go away? That thing's kind of annoying. How do I make that 4/3 right there go away? Fine. I don't like it. Tell me how to get rid of this.
Top row 3, 0, negative 2.
So top row, and you said what?
3, 0, and then negative 2.
So that's taking 3 of the first row plus 0 of the second row plus negative 2 of the last row. Ah, that did do it. That did work, by the way. That did work, but I'm gonna enforce something else. There has to be a 1 right there when you finish. So that will make a 0 there. So maybe I need to be more specific now. I want to keep that 1 right there. I don't want to get rid of that 1. I don't care what goes right there, but I definitely want the 1 and the 0. What row can I multiply by?
Could you do the same thing that we had in the bottom row?
So tell me what to write. There's going to be 3 numbers.
0, negative 2, and 1.
0, negative 2, and 1. Well, that would not affect that number. So 0 of that, 1 of that, and you said negative 2 of that. Yeah, that wouldn't give me a 0 there. How about this? How about 1, negative 4/3, 0. Is that going to work?
Yeah.
You took 1 of this row, negative 4/3 of that row, 0 of that row, and you add those together. Negative 4/3 times 1 plus positive 4/3 is going to make it a 0. And what is that going to be for that entry though? So negative 4/3 times that is positive 5/3 plus 4/3, so 7/3. 7. Surprisingly, it's not that bad, not that gross. And I guess like if we just left everything else the same like that, this doesn't change anything. It just keeps the middle row the same. We have our matrix that looks like this. It looks so close to what we need. Our goal was to make the identity matrix. So the new matrix that we multiplied by was so now all of this together is this. Okay, so 0, 7/3, 0, 1, minus 5/4, 0, 0, minus 9/2. Okay, so now I want that. I want one more product. Tell me how to do that. How can I for sure how can I for sure get the 1 right there? That's like that's an easy one. You only want to alter the 3rd row, right? You just want to, you don't need to add anything. You can just multiply something, you can divide by that to make it a 1. So you can do like, and then what? Divide by 9/2, that's like multiplying by negative 2/9. And that will make a 1 right there. How do I make that 0? Even if you might need some pen and paper for that one. Well, actually, we'll make it easy. I'll make it easy on you. We'll say that we didn't change anything else. Now all of that business. One last matrix. So now that's a 1. But I still need to zero out those entries. How can I do it? In one last multiplication. Come on, guys, this one's not bad. I just want to zero that and zero that and leave everything else the same. It's super easy, I promise. Someone tell me how to do it. Start talking. Just start making guesses. It's okay. But I want to hear you like actually making guesses here.
Would you just multiply it by 0?
But that multiply what by 0? Okay. What we want to do, the 1s were so useful to us earlier, right? When there was a 1 in the diagonal entry, we could zero out everything up and below it, above it and below it. So, like for example, the first row.
Negative 7/3, 0, 1.
So
Negative 7/3.
you got like that would make a 0, but then you're going to change that 1.
Yeah.
It's a lot easier than that. It's just 1, 0, negative 7/3.
Or would it be negative 7s?
Yeah, 1 of that, 0 of this, negative 7/3 of that, add them all together, you get rid of that 7/3.
Right.
So how do you get rid of the negative 5/4? Again, you're making use of that 1. So how do we get rid of it?
You could do 0, 1, 5/4.
That's it. And we don't want to change anything else. So what do we put in the last row?
0, 0, 1.
That's it. 1, 0, negative 7/3. I can't believe that I picked this matrix. Because it actually worked out nicely. And it has to do with the fact that somehow I picked the rows and columns of this matrix to have a special relation with each other. I forget what the original matrix was. It was that one. So that terminology we'll get to next time. But this is matrix factoring, basically. We have this matrix, and we're able to find a sequence of things to multiply it by to generate the identity. And well, why would that be important to us? Well, it means that we can solve systems of equations. The fact that we can do this, that we can generate this, means that we can solve systems of equations. And what do I mean by system of equations? Imagine that you have a feature vector that you're looking at, that you don't know the quantities for. And this vector, you're trying to find a solution to, say, this system. So like, suppose like, okay, never mind. So suppose you're an employer, you have, or a company, you have X1, X2, X3. You have 3 items that you sell, right? So, and it takes like 3 hours to manufacture X1, maybe 1 hour to manufacture X2, and maybe 4 hours to manufacture X3. And for some reason, you need, for compliance, the total number of hours per unit of these things needs to add up to like 10. Or actually, let's say plus 0 hours of X2 has to add up to 10. And then for each of these, each units of these items, it takes like 2 people to manufacture X1, 4 people to manufacture X2, and 1 person is like the manager to deal with X3. Perfect. And like this has to be equal to like to like 8 or something. Okay. And then finally, for compliance reasons, you have to like pay like 3 per unit for X1, and 2 per unit for X2, and 2 per unit for X3. And that cost has to be something like 11 or something. Okay. Now, how does this relate to what we're looking at? Well, this we can write as a matrix equation. This matrix equation. So how do we solve this system? What's one way that we can solve it? Well, we already did solve it. We can solve this right away. I don't want to because I've run out of chalk, or like I've run out of room, but what matrix is, so this is called the coefficient matrix, right? This, like, x1 times this column plus x2 times this column plus x3 times this column has to equal this. You see that here, right? There's x1, x2, x3, adding together to equal it. But where did this coefficient matrix come from? I wrote it this way because here, it's right here. This thing, that matrix that we started with. So what happens now is that we can multiply this on both sides of this equation. Multiply this, and then multiply this, and then multiply this, and then multiply by this, and then multiply by this on both sides of this equation. And eventually, what you'll get is this. I have no idea what the end result vector would be. It's just like, say B1, B2, B3. I don't know what you'll end up on that side, but once you have that, look what it says. Look what this product says. It says 1 times x1 plus 0 times x2 plus 0 times x3 equals B1. And then 0 times x1 plus 1 times x2 plus 0 times x3 is equal to B2. And then 0 times x1 plus 0 times x2 plus 1 times x3, that's equal to B3. Whatever the vector you get on this side after you multiply all of this, because we know that this multiplication gives us the identity matrix, which doesn't change anything. The matrix on the left will reduce the identity, and on the right we'll have a vector, and then the x's are just in plain sight. They're whatever you're left over with. Okay, so I don't know. Let me see. If I pull up, I think I have a Jupyter notebook open right now. And how long would this take me to do? It would take me like more time than I want to do during class. But I encourage you, like, if you have your notes down, you have NumPy, solve that system by just multiplying both sides of this equation by those matrices. Like, start with that one, then that one, then that one, then that one, then that one. And when you get the identity on the left, your solution is on the right. Those are the values for x that will satisfy that equation. Okay, so this is a fun little experiment we had today, a little game. But I did forget to mention one thing that's very important. But if you really understand how the matrix multiplication works, it should be clear to you that A times B is not equal B times A in general. It does not satisfy that property that you're very used to seeing. That's just something I forgot to mention, but it should be clear. In fact, sometimes you can multiply A times B, but you can't even, it's not even defined to multiply B times A, right? So, okay. So now, I think we should probably stop here, and I'm going to stop the recording here. I think this is enough of the matrix products.